Maybe it's night where you are and everything has finally gone still. Above your ceiling, past the quiet air and soft blue sky, the planets glide in silence. They loop around the sun, never drifting into the dark and never falling straight in, repeating the same hidden paths for billions of years. Tonight we're following a simple question with a huge impact. Why do planets orbit instead of floating away? We'll explore the gentle pull that never stops, the motion that never quite straightens, and the balance that turns falling into a graceful curve. Now breathe slowly, let your thoughts loosen, and drift into the quiet space where the planets move. Before we can ask why planets orbit, it helps to notice what an orbit actually is. When you draw one on paper, it looks neat and tidy, a perfect ring or a smooth oval. That picture is useful, but it can trick you into thinking the motion is tidy too. In real life, an orbit is not a picture. It's a path in three-dimensional space that a body follows over and over. The key idea is simple. An orbit is just a repeating path. The planet keeps moving. The path keeps repeating. Think about walking and throwing a ball for a second. If you toss a ball straight ahead while standing still, it arcs and lands a short distance away. If you toss it from a moving bike, the landing spot changes. The motion you see is the combination of the ball's forward motion and the downward pull of gravity. In space, the same two things are at work: a tendency to keep going forward and a pull inward toward a larger mass. Picture this. A planet is always moving forward along a tangent, like an arrow leaving a bow. At the same time, gravity from the sun is constantly tugging it inward. The forward motion wants to carry the planet away in a straight line. Gravity wants to pull it straight down onto the sun. The result is neither a straight escape nor a crash. It's a continuous curve, a graceful compromise where the planet keeps missing the sun again and again. A quick, very human way to see that compromise is with a rubber ball on a string. Swing the ball around your head and it wants to fly off in a straight line, but the string keeps it bending toward your hand. The string's pull is playing the role gravity plays in space. If you let go, the ball shoots outward. If you could magically cut the string and simultaneously remove the ball's forward motion, it would drop straight down. The orbit is the middle ground. Enough forward motion that the inward tug only ever bends the path, never ending it. Here's a thought experiment that Newton used to make this idea stick. Imagine a cannon sitting on a very tall mountain. If you fire a cannonball slowly, it falls to earth as any projectile would. Fire it faster, and it lands farther away. Now, imagine firing it fast enough that as it falls toward Earth, the curvature of Earth itself keeps dropping away beneath it. The ball keeps falling, but the ground keeps curving away at the same rate, so the ball never hits. It just keeps falling around the planet. That's an orbit. Perpetual falling that misses. If it helps, picture driving on a perfectly circular racetrack and trying to hold a steady speed. Your car wants to go straight because of inertia. Your steering wheel is constantly redirecting your motion to keep you on the circle. In space, gravity performs the steering. The car doesn't stop moving forward. Steering continuously changes the direction of that forward motion, and the combination is a loop. With planets, the loop is stable and repeats, because the forward speed and the inward pull are in a long-term balance. This balance can be delicate. Too much forward speed and the planet can escape the pull and drift away into a wider path, or even out of the system entirely. Too little forward speed and the tug wins, sending the object in tighter and tighter until it collides. Most planets exist in that in-between zone where forward motion and inward pull lastingly balance, a kind of forever fall that never quite arrives. Another thing to keep in mind, orbits aren't always perfect circles. Some are elongated ovals, called ellipses. That means the balance changes as the object moves. Sometimes it's a bit closer to the sun and moving a bit faster. Sometimes it's farther and moving slower. But over one complete trip, the motion repeats. Even the moon follows this rule around Earth, and artificial satellites like the International Space Station are also falling around Earth continuously. The ISS isn't above gravity, it's in free fall, moving forward fast enough that it keeps missing the ground. If your mind likes numbers, you can summarize the idea without diving deep into math. There's a speed needed at a given distance to keep that repeating path. That's the orbital speed. Closer in, where gravity is stronger, you need to go faster to avoid falling in. Farther out, you can go slower and still stay in orbit. But you don't need to memorize formulas to feel the concept. The backyard experiments and the cannon on a mountain image get the physics into your head in a way that's hard to forget. Try a tiny experiment next time you're near a playground. Spin a small bucket of water in a vertical circle and notice how the water doesn't spill when you swing it fast enough. The water is being pulled toward the bucket's center while its motion keeps it from flying straight out. It's not exactly the same as orbital motion, but it captures the same two-part dance: a pull inward and a push to go straight. The result is stability, where you might otherwise expect chaos. So, an orbit is a repeating path caused by a continuous tug inward combined with continuous forward motion outward. It's not a static ring drawn on paper. It's dynamic, an ongoing action. And it's not some cosmic magic. It's everyday concepts, inertia and gravity, interacting over and over. Once you see an orbit this way, as a forever fall that never quite arrives, the rest of the question becomes clearer. What sets the speed? How do different shapes of orbits form? And what happens when that balance gets nudged? We'll get into those next, but keep that image in your head. A planet that is always falling, yet never hitting. Think about the last time you dropped your keys. That tiny plunge from your pocket to the floor is the exact same sort of thing that keeps the Earth circling the sun. The same invisible rule at work on wildly different scales. Gravity is the quiet, ever-present reason things don't drift off into space. It isn't dramatic. It doesn't shout. It simply tugs, constantly. At its heart, gravity is simple. Every object that has mass pulls on every other object that has mass. That pull depends on two obvious things. First, how much stuff there is. The more mass an object has, the stronger its pull. Second, how close you are to it. The closer two things are, the stronger the tug between them. So a bowling ball pulls on you more than a tennis ball does. In practice, the difference is tiny. And the sun pulls on Earth enormously because the sun is unimaginably massive and, in cosmic terms, still relatively close. Because the sun is so massive, its gravity reaches far out into space and dominates our little neighborhood. That's why we call the planets neighbors. The sun's pull keeps them nearby. But gravity isn't a switch that turns on and off. It's always on. It is like an invisible hand that's constantly nudging each planet. every second, bending its path by a tiny amount. Over time, those tiny nudges shape the steady repeating tracks planets follow. A way to feel this is to watch someone toss a ball. The ball arcs and lands. That arc happens because gravity is pulling it down the whole time it's moving. Now imagine Earth itself as the ball, but with a massive sideways push. Earth is moving sideways very fast, tens of thousands of kilometers per hour. Gravity keeps pulling it inward toward the sun, but because Earth has that sideways motion, it never hits the sun. Instead, it's always falling around the sun, missing it, creating a stable orbit. So when you watch a ball fall, you're literally seeing the same physics that keeps planets in place, just on a scale you can hold in your hand. That constant tug shows up in ways you encounter every day. When you jump, there's a tiny, invisible countdown. You push off the ground, you coast upward for a moment, then gravity takes over and pulls you back down. Your weight, how heavy you feel when you stand on a scale, is just the measure of how strongly Earth is pulling you. If Earth pulled less, you'd feel lighter. If it pulled more, you'd feel heavier. And gravity is mutual. You pull on Earth just as Earth pulls on you. Only Earth is so huge that your pull does almost nothing to its motion. If you could stand on a very sensitive instrument and drop a bowling ball, both you and the bowling ball would move imperceptibly toward each other. That reciprocity is a key idea. Attraction works both ways. The reach of gravity can surprise you. The moon, sitting about 384,000 kilometers away, still tugs on Earth enough to create tides. The sun, much farther away, exerts an even larger tidal influence because of its sheer mass. Even when you climb a tall building, the change in gravitational pull is measurable, though tiny. You're a few meters farther from Earth's center, so the pull is fractionally weaker. In space, where things seem weightless, it's not because gravity has switched off. The International Space Station and its astronauts are in free fall around Earth. They're constantly falling toward Earth, but because they're moving sideways so fast, they keep missing it. The same falling around idea as planets. That's what creates the sensation of weightlessness. Distance matters in a dramatic way. If you move twice as far from an object, the pull shrinks a lot. That's why the sun's gravity, despite its reach, becomes less dominant the farther you go, and why the gravitational effect of small things like mountains or cars is negligible for most purposes. But close enough, mass really counts. A planet-sized object has enormous gravity. A pebble, almost none. One helpful image is to imagine space as a stretched trampoline and massive objects as heavy balls placed on it. Each ball makes a depression. Smaller balls nearby roll toward the depression. The trampoline analogy has its limits. Gravity doesn't need a fabric to bend, and it acts in every direction, but it gives a feel for how mass changes the shape of space and guides motion. The important takeaway is that orbits aren't magic highways. They're continuous responses to a persistent pull. Knowing gravity is always at work changes how you think about motion. When engineers send probes to Mars or snap a satellite into orbit, they're planning with that constant pull in mind. They give a spacecraft just the right sideways speed so it will fall around a planet instead of crashing into it. When you step off a cliff and, please don't, imagine the drop. That fear is a very human response to a force you feel every day, but rarely show respect for. Gravity keeps your feet on the ground, makes walking predictable, and, on a grander scale, sculpts the architecture of the solar system. So the next time you drop something, jump, or gaze at the moon, remember, you're witnessing the same gentle, relentless pull that has kept Earth and its fellow planets dancing around the sun for billions of years. That persistent tug, simple, unwavering, universal, is the reason the cosmos feels both orderly and alive. Now that we've felt gravity's constant hand, let's look closer at how that tug turns into the different shapes and speeds of orbits. The other part of the story is inertia, the tendency of an object to keep moving in a straight line at the same speed unless something changes it. Think of it this way. If there were no forces at all in the universe, no gravity, no friction, nothing, every planet, every moon, every stray rock would simply drift away in a straight line forever. There's nothing in motion that wants to turn. Motion wants to keep going as it is. Imagine you're riding a skateboard down a straight path. You push off, you glide, and if no one and nothing touched you, you'd just keep gliding at the same speed forever. But in the real world, tiny forces like air resistance and tiny bumps slow you down. In space, though, those small annoyances are mostly absent. So if you were floating in a spaceship and shut off the engines, you wouldn't slowly drift to a stop. You'd coast in the same direction and at the same speed until some force changed that motion. Here's where the dance between inertia and gravity comes in. When Earth zips around the sun, inertia is constantly trying to make it move in a straight line off into space. Gravity, on the other hand, pulls Earth inward toward the sun. The orbit we see, the path Earth takes, is the result of those two competing influences balancing out. Imagine pushing a ball on a string. Your hand's pull is like gravity, bending the ball's path inward. The ball's forward motion is like inertia, wanting to fly away tangentially. The combined motion becomes circular or elliptical. Let's make it more personal. I remember the first time I really understood this. I was on a small amusement park ride where a round platform spins and the floor drops away. You're pinned to the wall by your motion. If the wall weren't there, you'd fly off in a straight line. The platform provides the inward force that bends your otherwise straight path into a circle. That feeling, wanting to keep going straight while something pulls you inward, is exactly inertia versus centripetal force in miniature. Visualize an orbit for a moment. At any instant, the planet has a velocity vector, an arrow showing the direction it would travel if nothing pulled on it. That arrow points tangent to the circle. Now imagine gravity as a continuous inward tug from the sun. Each instant, the planet wants to go straight. Gravity bends that straight path a tiny bit toward the sun. Over and over, those tiny bends add up into a curved path, an orbit. The shape of that orbit tells you how inertia and gravity match up. If a planet is moving very fast, if its inertia is strong, those straight line tendencies stretch the path outward. It will move farther from the sun at points in its orbit. If gravity is stronger relative to that motion, the path curves inward more tightly. When they balance in the just right way, you get a smooth repeating path like a circle or ellipse. If inertia overpowers gravity completely, the object escapes. Think comets that swing by and then speed away into interstellar space. If gravity dominates, the object spirals inward and crashes. You can see this play out at home with a simple experiment. Take a small ball attached to a string and whirl it around in a circle. The string is acting like gravity. It provides the inward force. If you whirl faster, you'll feel the ball pulling harder on the string. That's stronger inertia, trying to keep the ball moving straight. If you let the string go, the ball shoots off tangentially in a straight line. That snap-away moment shows how inertia always wants to keep the existing motion. Another everyday example is driving and taking a turn. When you turn left quickly, you feel your body push to the right, not because something is pushing you that way, but because your body wants to continue the straight line motion you had before the wheel turned. Seatbelts and friction provide the forces that change that motion and keep you in the car. In space, there's no seatbelt or friction. The natural result of inertia and gravity is the elegant, predictable orbits we observe. Astronauts experience a surprising consequence of this balance: weightlessness. People often say astronauts float because there's no gravity up there. That's not quite right. Gravity at the altitude of the International Space Station is still strong, more than you'd expect. Astronauts float because they are in continuous free fall. Their spacecraft is falling toward Earth due to gravity, but it's moving sideways fast enough that the surface of the Earth curves away beneath it. Inertia keeps the spacecraft moving forward. Gravity bends that motion into an orbit. The result? Everything inside is falling together, and the astronauts feel weightless. This balance also explains why some orbits are stable and repeating while others are not. If an object's speed and direction are tuned to match the pull of the central body, it will keep looping in a predictable path. Speed it up a bit, and the path bulges outward, maybe turning an ellipse into an open trajectory that never returns. Slow it down, and the inward tug wins, potentially pulling the object into a collision. That simple interplay, one force trying to keep it straight, the other trying to pull it in, governs everything from the planets in our solar system to artificial satellites and space debris. So the next time you watch a satellite glide across the sky or feel that push to the side when you make a sharp turn, remember, what you're sensing is inertia, the universe's stubborn insistence that motion keep going. Gravity is the negotiator, the steady hand pulling things inward. Together, they choreograph the cosmic dance that keeps planets circling, moons orbiting, and us, whether on a skateboard, in a car, or in a spaceship, firmly aware of the physics that govern motion. Cut to animation, a planet moving in a straight line, then gravity vectors pulling it into a curved orbit. Overlay labels inertia and gravity. Then show the ball-on-string demo in slow motion and a clip of an astronaut floating in the ISS to tie the concept to real-world and space examples. Prompt to camera. If you want to try a safe hands-on test, tie a small ball to a shoelace and swing it gently. Let go at different points and watch the path it takes. Tell me what you observed in the comments. Did it fly off tangent, curve inward, or both? Now picture this. You're standing on top of a tall mountain with a friend, a bright blue sky above, and a valley rolling away below. In your hand, you've got a rock. Or maybe for those of us who never grew out of childhood, a baseball. You lob it gently over the edge. It arcs and lands not far away. You throw it harder next time. It flies farther before it thuds on the dirt. Each throw makes the landing spot wander a little more down the mountain slope. Keep doing that in your head, But imagine that the mountain is the size of a planet, and there's no air to slow the rock. If you could somehow throw it extremely fast, something surprising would happen. Instead of ever hitting the ground, the rock would just keep falling and falling, but at the same time it would keep moving forward. The curvature of its fall would match the curvature of the planet below. The rock wouldn't collide. It would simply fall around the planet, forever tracing a path that bends but never connects to the ground. That, astonishingly, is what an orbit is. This mental image of throwing a ball off a mountain until it's thrown so fast it never lands is one of the simplest and most useful ways to picture orbital motion. It's not magic. It's just two simple facts playing out together. Gravity pulls you inward, and inertia keeps you moving in the direction you are already traveling. When those effects are balanced just right, the inward pull from gravity never manages to catch up with your sideways motion. The result is a continuous fall that wraps around instead of ending in a collision. Isaac Newton imagined this exact setup in a famous thought experiment often called Newton's cannon. Picture a very, very tall mountain. Put a cannon on top, load it with a cannonball, and fire. Fire it gently, and the cannonball drops and hits the ground nearby. Fire it harder, and it flies much farther. Fire it fast enough, and here's the kicker. The ground curves away below the cannonball at the same rate it falls. The cannonball keeps missing the ground, and it goes into orbit. That fast enough idea is where a lot of people imagine something mystical, as if the planet is doing some special trick to keep satellites up. But really, planets are constantly in the same situation as that cannonball. Take Earth around the Sun. The planet is constantly being tugged inward by the Sun's gravity. At the same time, Earth is zipping sideways at about 30 kilometers per second. That lateral speed is enormous, roughly 108,000 kilometers per hour. Because of that sideways motion, Earth is always falling toward the Sun, but never getting any closer in a way that results in a crash. It just keeps missing. This makes orbit a very different word from the casual way we might use it. When you hear orbit, you might picture a smooth, circular track drawn in space. Orbits can be circles, sure, but more often they're ellipses, stretched out loops. The shape depends on the balance between speed and gravity. Too slow and you spiral inward. Too fast and you break free and fly off into space. The sweet spot makes you fall around the Sun, again and again, in a graceful, repeating path. One thing people often get wrong is the idea that orbiting objects are gravity-free. Astronauts on the International Space Station look like they're floating because they are. But floating, in this case, means they're in freefall. The station and everything inside it are falling toward Earth, but because they're moving sideways so quickly, they keep missing the ground. That creates the feeling of weightlessness. So weightlessness isn't the absence of gravity, it's the sensation that comes from constantly falling without ever striking down. You can see similar behavior closer to home with artificial satellites. We launch satellites and give them sideways velocity. Once they have enough horizontal speed, gravity keeps them curved around the planet in a steady orbit. Adjust their speed a little and their orbit changes. Lower speed drops the orbit closer to Earth. Higher speed pushes it out into a higher, slower path. Tweak it enough, and you can escape Earth entirely. If we go back to our Sun and the planets, that sideways motion is the legacy of how the solar system formed. Billions of years ago, a spinning disk of gas and dust collapsed under gravity. as pieces of that disk aggregated into planets. They inherited the sideways motion of the rotating cloud. So each planet didn't set out to balance the sun's pull so much as it started with a particular speed and trajectory. Gravity then bent that straight-line motion into the orbital paths we see today. They're all forever in a kind of cosmic fall, but their initial sideways motion keeps them in graceful motion around the sun. Making this personal helps the idea stick. Think about riding a car around a circular roundabout. If you're going slowly, you'll be pulled slightly toward the inside edge because of the turn. Go faster, and that pull becomes stronger. You feel pushed outward against your seatbelt, which is actually providing the inward force needed to keep you on the curve. In space, there's no seatbelt. Instead, gravity is the inward force that curves your path. Your inertia always wants to carry you in a straight line, but gravity continually nudges you inward, so your straight line path turns into a curved orbit. The balance between falling and moving sideways is also why orbits can change. If something slows a planet or satellite, a tiny bit of drag from a planet's atmosphere, a gravitational pull from another body during a close pass, the orbit alters. For satellites around Earth, that's why some low orbits eventually decay and the objects burn up. Tiny friction with the residual atmosphere removes sideways speed, and the satellite spirals down. For the planets, occasional gravitational nudges from other planets or asteroids can pump their orbits into new shapes over very long timescales. So when you picture Earth racing around the sun, don't imagine it as a little marble glued to an invisible track. Instead, imagine Earth in a continuous, unending fall, but with such an enormous sideways velocity that the fall never reaches the sun. It's a beautifully simple dynamic, a tug inward, a motion sideways, and the resulting path that lets planets circle the sun for billions of years without ever hitting it. Let's hold that image for a moment. Everything in orbit is essentially falling, but with a sideways speed that keeps the fall from ending. With that in mind, the next question becomes, how do those small differences in speed and direction make such different kinds of orbits? If gravity is always pulling inward, you might think the planets should be slowly spiraling into the sun, like leaves falling toward a drain. But that's not what we see. The reason is simple and kind of beautiful. As long as no meaningful energy is taken away from a planet's motion, the tug of gravity and the planet's sideways speed stay in a steady dance. Let me explain that in a way you can picture. Think of a runner on a circular track. If they run at just the right speed, centrifugal forces from their forward motion balance the inward pull of making the turn, and they stay on the lane without drifting inward. If they slow down, their path tightens, and they might stumble toward the center. If they speed up too much, they could fly outward. Planets work the same way. The sun's gravity pulls inward, and the planet's tangential motion, its sideways velocity, tries to carry it straight. The result is an orbit. As long as nothing robs the planet of energy, that balance stays intact, and the orbit persists. Why don't planets lose energy? The immediate answer is that space is an excellent vacuum. There's almost nothing for a planet to push through. On Earth, when you drive your car, friction with the air and road constantly saps energy, and you have to refuel. In space, there's no thick air to push against. There's almost no friction to steal a planet's speed. So unlike a bicycle that slows down on a long ride if you stop pedaling, a planet doesn't gradually lose momentum just by coasting through empty space. To make this concrete, imagine spinning a ball on the end of a string. If the string doesn't break and you don't let go, the ball keeps circling. The string's tension is like gravity. It pulls inward while the ball's motion tries to fly outward. If the string frays or you cut it, the ball's behavior changes radically. In the same way, if something removes kinetic energy from a planet, a frictional force, a collision, or a torque, then the orbit can change. But in the near-perfect vacuum of the solar system, there's usually nothing to do that on short timescales. There are, however, tiny mechanisms that do change orbits, but they act very slowly or mostly affect small bodies. For satellites close to Earth, the thin upper atmosphere still produces drag, and without occasional boosts, they slowly spiral down and burn up. For asteroids and dust grains, radiation from the sun, or tiny pushes from uneven heating, the Yarkovsky effect, can shift their paths over millions of years. For entire planets, the main drivers of change are subtle gravitational nudges and tidal interactions. Tidal effects are worth a quick pause because there's something you can relate to. You've probably seen how Earth's oceans bulge toward and away from the moon. That's a tidal effect. Tides transfer energy and angular momentum between bodies. The Earth-Moon system, for example, is slowly changing. Tides raised on Earth by the moon are dissipating energy and causing the moon to very gradually recede, while Earth's rotation is slowing. But for a planet orbiting the sun's tides on the planet and the planet's tides on the sun are tiny, unless the planet is very close. For Earth, the net effect on the orbital distance is extremely small over human timescales. Gravitational interactions between planets can also nudge orbits, especially when bodies pass relatively near each other. These perturbations are responsible for the very slow, complicated drifting and precession of orbital paths. Over billions of years, they can even lead to chaotic outcomes in some systems, where a planet might be nudged into a different orbit, or, in extreme cases, ejected. But again, these processes are gradual. On the time scale of our lives, or even the lifetime of human civilization, the major planets' orbits are essentially steady. Another interesting long-term effect comes from the sun itself. It's slowly losing mass. Through the solar wind and by radiating energy, the sun sheds mass, and as it does, its gravitational pull weakens ever so slightly. That causes planetary orbits to expand outward imperceptibly. So, paradoxically, the sun's slow mass loss actually makes planets drift outward over vast timescales, not inward. You might also have heard about general relativity and Mercury's precession, the subtle way Mercury's closest point to the sun shifts over time. That's a correction to the orbit's orientation, not a quick inward spiral. Even that relativistic effect changes the shape and orientation of the orbit more than it drains orbital energy. It helps to compare different environments. Low Earth orbit satellites need periodic boosts because of atmospheric drag. A comet passing through the inner solar system can lose gas and dust and have its trajectory altered by jets of escaping material. But Jupiter, Earth, and the other planets are huge, moving in nearly empty space, and they don't have air braking them. So unless they collide with something massive or experience a very strong tidal exchange, they'll keep circling. So, to bring this home, A planet falls toward the sun due to gravity, but because it's also moving sideways fast enough, it keeps missing the sun and instead follows an orbit. In the near-perfect vacuum of space, there's nothing substantial to take away the planet's energy, so that orbit continues. Tiny effects do nudge and change orbits, and over the eons those small nudges add up. But on the scale of lifetimes, centuries, even millennia, planetary orbits are remarkably stable. It's like watching that runner on the track. Unless the track changes or the runner's legs get slower, the lap keeps going round and round. So what would it take for a planet to simply drift away, to unhook itself from the sun and float off into space? The short answer is speed. There's a very specific speed threshold that separates stuck to the sun from free to go, and that threshold is called escape velocity. Think of escape velocity like the magic pace on a treadmill you'd need to match to stop being pulled back by its belt. If you run slower than that pace, the treadmill will eventually haul you back to the center. If you somehow sprint faster than the required speed, you'll keep moving forward and never be dragged back. For gravity, escape velocity is the speed where the sun's pull can no longer turn you around and pull you back into orbit. A simple way to picture it at home: toss a ball straight up. If you throw it gently, gravity pulls it back and it falls in your hand. If you throw it harder, the ball goes higher, but still returns. Only if you could throw it ridiculously fast, much faster than you ever can, would it never return. For planets, that ridiculously fast number is huge, and they simply don't have it. Here's the physics in everyday language. Gravity is doing two things. It wants to pull you inward, and your sideways or forward motion wants to carry you onward. If you're moving slower than escape velocity, gravity eventually bends your path into a loop, an orbit, or sends you spiraling inward. If you're moving at escape velocity or faster, you can climb away forever. You won't speed up. In fact, gravity still pulls and slows you, but you'll slow asymptotically toward zero speed at infinite distance, never turning back. Every location in space has its own escape speed because gravity weakens with distance. The sun's escape velocity near Mercury's orbit is much higher than it is out near Neptune. The closer you are to a massive object, the harder it is to break free. That's why the escape speed from the surface of Earth, the speed a rocket needs to reach to never fall back, is about 11.2 kilometers per second. The escape speed from the sun at Earth's distance is bigger, roughly 42 kilometers per second. Earth itself, while zipping around the sun at about 30 kilometers per second, falls short of that solar escape speed. So, even though Earth is moving really fast, it isn't quite fast enough to break up with the sun. Let's translate that into feelings. Picture Earth on a long leash tied to the sun. That leash is invisible, but strong. The faster Earth goes, the more stretched the leash is, and the wider its circle around the sun becomes. But to actually snap that leash and drift away into the dark, Earth would need an extra burst, a shove, big enough to push it past escape velocity. Nature didn't give planets that shove under normal formation conditions. Instead, planets were born into a comfortable mutual dance with their star. There's also a helpful energy perspective that keeps the idea intuitive without heavy math. An object's energy is the sum of how fast it's moving, kinetic energy, and how deep it sits in a gravity well, potential energy. If the total energy is negative, the object is bound. It can't escape. If it's zero or positive, it's free to go. Escape velocity is exactly the speed where that total energy becomes zero. Below that, you're tied down. Above it, you're free. This explains why comets can behave so dramatically. Some comets fall toward the inner solar system on stretches of orbit that are still bound. They loop in and out. But some comets, or spacecraft like some of the early interplanetary probes, can exceed escape velocity during close gravitational encounters and be launched on hyperbolic, unbound trajectories that take them away forever. Voyager 1 and 2 are examples of human-made objects now on trajectories that exceed the sun's escape velocity, sent on their way by careful launches and gravity assists. It's also why planets tend to stay put for billions of years. They move fast enough to avoid falling in, but not fast enough to escape. That makes their relationship with their star a stable, long-term partnership. Of course, it's not an unbreakable marriage. Gravitational nudges from other planets, passing stars, or the slowly evolving dynamics of a system can sometimes change orbits drastically over very long timescales. A planet can be kicked into a new path, or even ejected entirely in rare, violent cases. But for the most part, the solar system's planets are in steady orbits because they don't reach the sun's local escape speed. Now, a couple of concrete touchstones to keep this from feeling too abstract. Earth orbits at about 30 kilometers. The sun's escape speed at Earth's distance is about 42 kilometers. Mercury, being closer, needs a much higher speed to break free. It orbits around 47 kilometers, and the sun's escape speed there is roughly 66 kilometers. Out at Neptune, orbital speed drops to about 5.4 kilometers, and escape speed is only around 7.6 kilometers. That drop with distance is why outer objects can more easily be nudged into escape orbits by interactions than inner planets. The gravitational leash is weaker. And what about the planet's own local escape speeds? Each planet has its own gravity well, and that defines how hard it is to escape from the planet itself. For example, if you want to escape Earth's gravity from the surface, you need around 11.2 kilometers. From the Moon, it's only about 2.4 kilometers. That's why launching from the Moon is so much easier. But escaping a planet doesn't guarantee escape from the Sun. Once in space, you still must contend with the star's pull and the tricky ballet of orbital mechanics to reach the Sun's escape threshold. In everyday life terms, think of the difference between leaving a party and leaving your hometown. Leaving the room, escaping a planet, takes a little effort. Walk out the door. Leaving the town, escaping the sun, requires packing a car, hundreds of miles, maybe a few fuel stops, a much bigger commitment. The planets haven't packed up to leave town. They're content circling the block. So, when we ask why planets don't float off, the real reason is simple and elegant. They're not moving fast enough. They're in the Goldilocks zone of motion, fast enough to avoid falling in, slow enough to stay bound. And that balance is what makes planetary systems peaceful, ordered places, rather than chaotic gatherings of runaway worlds. For the Sun and its planets, it's a relationship built on just the right amount of speed. Think about the little orbit diagrams you saw in school. neat circles with tiny planets glued to them like beads on a bracelet. They're tidy and satisfying. But in real life, planets don't march around the sun in perfect circles. They follow ellipses, ovals, a touch stretched or sometimes noticeably elongated. That detail changes how a planet speeds up and slows down, where it's closest and farthest from the sun, and even the way we model planetary motion. Imagine you're swinging a ball on a string over your head. If you hold the string perfectly taut and walk in a perfect circle, the ball traces that circle. But if you step a little faster or let the string swing outward, the path shifts. It stretches into an oval. The forces are the same. Your hand pulls inward, the ball keeps moving forward. The balance between those two creates the path. That's basically what gravity and motion do for planets. Kepler noticed this in the 17th century. He didn't just guess. He studied decades of observations and found that planets sweep out ovals, not perfect circles. Newton later showed why. The gravitational pull from the sun and the planet's inertia, its tendency to keep going straight, combine to make a closed, repeating path that's an ellipse when the energy and angular momentum are in a particular range. Small changes in speed or direction at one moment can stretch the path, but it still loops back on itself. Let's make that a little more picture-friendly. Visualize an ellipse as a squashed circle. It has two focal points inside it. And here's a key point. The sun sits at one of those foci, not at the center. So when a planet is at one end of its orbit, it's a bit closer to the sun than when it's at the opposite end. The nearest point is called perihelion. The farthest is aphelion. Earth's perihelion is only about 3 million miles closer than its aphelion. Not a massive difference, but for other objects, the gap can be huge. Eccentricity is the number that measures how stretched an ellipse is. An eccentricity of 0 is a perfect circle. Tiny numbers mean nearly circular orbits. Larger numbers mean long, skinny ovals. Most of the major planets sit close to 0. Earth's eccentricity is about 0.017, which explains why our orbit looks almost circular. Mercury, on the other hand, has an eccentricity of about 0.205, so its distance to the Sun changes a lot during one lap. And then there are comets and some dwarf planets with eccentricities near 1. They zoom in from the outer solar system on highly elongated trips. Here's another part that's beautiful and surprisingly relatable. The speed of a planet changes along that ellipse. When the planet drops closer to the sun, the sun's gravity tugs harder, and the planet speeds up. When it's farther away, gravity's pull weakens and the planet slows down. That's Kepler's second law. The planet sweeps out equal areas in equal times. If you draw a line from the sun to the planet, that line covers the same area in a fixed interval, whether the planet is rushing past perihelion or drifting near aphelion. Put simply, it goes fast when close, slow when far. You might wonder, if the path stretches and speeds shift, why doesn't the planet just fly off or spiral into the sun? That's where the concept of balance comes in. Think of a car on a curved track. If you're driving too fast around a bend, you skid outward. Too slow, you slide inward. For planets, too fast or too slow would mean enough extra or missing energy to change the type of orbit, potentially turning a closed ellipse into an open parabola or hyperbola. But as long as the planet's total energy keeps it bound to the sun, every point on its path reflects that same balance between the inward gravitational pull and the inertia that wants to fling it outward. The orbit might be more or less stretched, but it remains a repeating loop. A quick personal memory. The first time I learned about perihelion and aphelion, I thought, so seasons must be because we're closer to the sun? That seems straightforward. Closer equals warmer. But then someone pointed out Earth is actually closest to the sun in January, during the Northern Hemisphere's winter. The real reason our seasons change is tilt, not distance. Still, that initial confusion helped me appreciate how subtle these orbital details can be, and how they often defy our everyday intuition. Let's put this into perspective with a few examples you can visualize on screen. Earth, nearly circular, small eccentricity. Our year feels steady because distance to the sun barely wobbles. Mercury, noticeably elliptical, so its temperature swings and orbital speed vary more across an orbit. Halley's Comet, extremely eccentric. It spends most of its life out near the depths of the solar system, then swings in close for a brief blazing visit. If you're scripting visuals or B-roll, this is a great place for dynamic graphics. Show a circle turning into an ellipse as you nudge the planet's speed. Demonstrate the sun sitting at one focus. Animate a planet speeding up as it nears perihelion and slowing at aphelion. Overlay the terms perihelion and aphelion as the planet passes those points, and add a simple arrow showing velocity changes. A split-screen comparison of Earth and Mercury helps viewers grasp how eccentricity changes the look and tempo of an orbit. There's also a human angle to this science. The fact that orbits are ellipses reminds me of how life rarely runs in perfect circles. We make plans that almost work out, then something nudges us off course. Small differences in timing, speed, or direction, and we end up on a slightly different path. Yet, like planets, we're still held by balancing forces, habits, responsibilities, relationships. The path might stretch, get closer to what pulls us in, pull us farther away. We adapt, and the loop repeats. Not identical, but bound by the same basic rules. To wrap this piece, ellipses are the natural shape that emerges when gravity and motion interact honestly. They're a small tweak from the tidy circles we doodle, but that tweak carries real consequences for speed, temperature, and time spent near the sun. Understanding ellipses gives us a more accurate map of the solar system, and it also gives a neat metaphor for life's slight deviations and the balances that keep us in orbit. Think about the picture you've been holding in your head so far, a planet tracing an elegant path around the sun. But that image is only one layer of a much richer scene. Orbits aren't a solo performance, they're an entire family act. Moons orbit planets. Tiny rocks sometimes orbit those moons for a while. Dust makes its own loops in rings. Each of these bodies is doing the same balancing trick, moving forward and being pulled inward by gravity. And as a result, they trace a path instead of just drifting away. Imagine standing on a playground watching a kid swing a yo-yo on a string. The yo-yo wants to fly straight, but your hand tugs it inward, and the result is a circle. Replace your hand with gravity, the yo-yo's forward motion with sideways speed, and you have the basics of orbital motion. A moon is being tugged inward by its planet, and, at the same time, has enough sideways motion to miss crashing into the planet. Instead of falling straight down, it falls around, and around again. That's why the moon keeps circling Earth, and why Io, Europa, and Ganymede keep circling Jupiter. The nested nature of these motions is one of the universe's most satisfying patterns. A moon goes around its planet. The planet goes around the sun. The sun itself orbits the center of the Milky Way. At each level, the same simple idea repeats. Forward motion plus gravity makes curvature. Curvature makes a loop. Think of Russian nesting dolls. Each orbit sits inside a larger one. Or think of concentric gears. The motion of the small gear depends on the bigger gear, and vice versa. Nothing floats alone. There are some beautiful real-world examples that bring this nesting to life. Take Earth and its moon. The moon circles Earth, but both together orbit the sun. If you track the moon's path relative to the sun, it wouldn't be a perfect circle. It's a complicated braided path that reflects the pull of the sun and Earth together. The center of mass of the Earth-Moon pair, the barycenter, sits just beneath Earth's surface, and Earth itself does a tiny orbit around that point. In a sense, Earth and Moon are partners in motion. Not all satellites are as big or stable as our Moon. Some are tiny, and some are only satellites for a little while. In 2006, astronomers spotted an object called 2006 RH-120 that got temporarily captured by Earth's gravity. It danced around us for about a year before slipping back into a solar orbit. These temporary captures are like a stray dog deciding to follow you for a night before wandering off. Near-Earth space occasionally gathers objects briefly, and they remind us that gravity's net isn't perfectly tidy. Then there are oddball orbits that defy our everyday intuition. Some objects share an orbit with a planet, but don't crash into it because of clever balancing acts, quasi-satellites, and horseshoe companions. 469219. Kamo Owalawa, for example, is a tiny quasi-satellite of Earth. It doesn't orbit Earth the way the Moon does, but it stays near us in a looping pattern as both travel around the Sun. Around Saturn, Janus and Epimetheus share almost the exact same orbit and perform a slow orbital dance where they swap positions every few years. It's like two skaters circling the rink and trading places while keeping the same path. Rings are another tiny orbit phenomenon that's easy to miss from far away but spectacular when you zoom in. Saturn's rings are made of countless particles, each individually orbiting Saturn. Some of those particles are shepherded into narrow bands by small moons. Those shepherd moons keep the rings sharp, nudging particles with their gravity. In some cases, a moon can be so close to its planet that tidal forces begin to pull it apart. And if a moon crosses its planet's Roche limit, it can be torn into countless fragments that spread into a ring. So, rings and moons are part of the same toolbox. The same forces that make moons can make rings, and the same interactions can turn moons into rings again. What's beautiful about this nesting is how scalable the idea is. The same rule that keeps a rock orbiting a moon keeps the moon orbiting a planet, and the planet circling a star. Scale up again, and whole star systems orbit the center of a galaxy. It's a fractal of motion. The same theme in different keys. That's why understanding orbits at one level helps you predict behavior at another. There's also a deeply human angle to this. When you drive through a roundabout, you're doing a tiny version of what planets and moons do. You enter with a forward speed. The curve of the road and the friction of tires keep you from flying off into the flower bed. Traffic lanes nest, merge, and split, just like orbital paths. A bicyclist might circle a plaza while cars circle the larger road around it. And the city itself sits on a planet that circles the sun. We live inside a hierarchy of motion all the time, and most of our daily movements are governed by the same balancing acts. Orbits are not always eternal. Over millions of years, interactions can change them. Tidal forces can slow a moon until it moves outward or inward. Collisions can kick fragments into new orbits, creating rings or spawning new moonlets. Gravitational perturbations from passing bodies can nudge an object into a new track or fling it out of the system entirely. Phobos, one of Mars' moons, is spiraling slowly inward and may someday break apart to form a ring around Mars. That slow drama is unfolding at a pace our lifetimes rarely notice, but it's the same dynamic behavior that has shaped the solar system for billions of years. Try imagining what sunrise would look like from a moon orbiting a gas giant. The planet would dominate the sky, rotating silently while the star peeks out from the side. If you were standing on a little moon near Saturn's rings, you might watch ring particles pass overhead like slow meteor showers. These aren't abstract ideas. They're real sights somewhere out there. Scenes created by the same simple push and pull that keeps you in your seat on a moving bus. So when you next picture an orbit, don't stop at the single curve around a star. Picture the layered nest, pebbles circling moonlets, moonlets dancing around planets, planets tracing paths around stars, and those stars gliding around galactic centers. At every level, forward motion and gravity conspire to turn straight-line motion into patterns, repeated, nested, and interconnected. It's a cosmic choreography that reminds us that motion is rarely lonely. Everything is part of a larger dance. Now, let's zoom in on the small, almost invisible nudges that are always at work in a planetary system. You probably picture planetary orbits as tidy, unchanging ellipses, and on the scale of our lives, and even of civilizations, they are remarkably steady. But steady doesn't mean frozen. Tiny disturbances are constantly tugging, pushing, and whispering to these worlds, and over long stretches of time, those whispers add up into noticeable changes. Think of it like a crowded dance floor. Each dancer, every planet, swings around the central stage, but every now and then someone brushes past you. That gentle bump doesn't send you flying across the room, but if it happens enough times, your path across the floor subtly shifts. In the solar system, every planet pulls on every other planet. Jupiter's gravity tugs on Mars, Earth tugs on Venus. Even distant Neptune gives Pluto a long, slow handshake. These mutual gravitational pulls slightly stretch or tilt orbits, changing the shape, how oval an orbit is, the tilt, the inclination, and the orientation, where the closest approach to the sun happens. Most of these changes are minute from day to day, but accumulate over millions to billions of years. Then there are influences that come from the sun itself. The sun is losing mass, not in dramatic bursts, but continuously, as it converts a tiny fraction of its mass into light and ejects particles in the solar wind. Less mass in the center means a weaker gravitational grip, so orbits very slowly expand outward over vast timescales. It's a whisper that, given enough time, you can detect. Light itself is another actor. Photons carry momentum, and when they scatter off small particles, dust grains, tiny meteoroids, they exert a faint push. For dust, this can be a big effect. Sunlight can blow small particles outward, or, via the Poynting-Robertson effect, cause them to slowly spiral toward the sun. For full-size planets, the push from light is negligible, But for the tiny debris left over from planet formation, it helps sculpt rings and disks. Gas plays a similar role in young systems. When planets form, they often sit in a disk of residual gas. That gas exerts drag, and even a gentle drag can make a forming planet migrate inward or outward. That's one of the reasons we see exoplanet systems with planets in positions that would have been hard to explain if everything had stayed put. Migration early on rearranges the board. All these influences, gravitational tugs, solar mass loss, radiation pressure, gas drag, change what astronomers call the orbital elements. An orbit's semi-major axis, its average distance from the Sun, can shift. The eccentricity, how circular or oval the path is, can grow or shrink, and the inclination, how tilted the orbit is, can wobble. Orbits also precess. The orientation of an ellipse slowly rotates, so the point of closest approach to the Sun moves around like the slow hand of a clock. Why don't these changes fling planets off into space? Because the Sun's pull is overwhelmingly dominant. If you try to push a heavy boulder with your hands, tiny nudges won't do much. The Sun is the boulder. Most disturbances are gentle compared to the primary gravitational grip that keeps planets bound. So, while orbits shift, they remain gravitationally tied to their star. Night to night, the sky is serenely constant, and even across a human life, the planets trace nearly the same well-worn paths. Still, gentle doesn't mean unimportant. Because these nudges are persistent, they can lead to significant rearrangement given enough time. Resonances are a great example of how small forces can amplify one another. When two bodies have orbital periods that are simple ratios, say one planet going around twice for every 3 circuits of another, their repeated alignments mean their tugs add up in the same rhythm. Resonances can pump up eccentricities and tilts, clear out regions of space. We see this in the asteroid belt's Kirkwood gaps, or lock bodies into stable, synchronized dances, as Pluto is locked with Neptune in a graceful 3.2 resonance that keeps them from colliding despite their crossing paths. Then there's chaos. Chaos in this context doesn't mean explosions or sudden disaster. It means that small differences in starting conditions can lead to very different outcomes given enough time. In some parts of planetary systems, especially where multiple resonances overlap, the orbital evolution becomes chaotic, unpredictable beyond some timescale. Over hundreds of millions to billions of years, that unpredictability can lead to planets scattering outward, plunging inward, or even being ejected into interstellar space. Computer simulations show that entire systems can rearrange themselves, swapping planets between inner and outer zones, or losing members entirely. It's not common on human timescales, but on cosmic timescales, it's part of the story. We also see practical evidence of long-term change beyond our own backyard. Many exoplanet systems contain hot Jupiters, gas giants sitting scorchingly close to their stars. The most plausible explanation is that these giants formed farther out and migrated inward, carried by interactions with gas disks or through gravitational disagreements with other planets. The variety among exoplanet systems tells us that style of evolution, slow nudges turning into dramatic reconfigurations, happens across the galaxy. If you've ever watched a long movie and noticed how a subplot builds quietly until it changes the whole plot. That's what these tiny forces do. Each force on its own is subtle, but their combined effect across eons can be decisive. Yet even with these slow changes, there's a comforting constancy. From night to night, the planets rise and set where we expect, calendars hold up, and ancient sky stories still line up with what we see. The cosmos manages to be both dynamic and dependable. On a personal note, I like to imagine standing under a clear, starry sky and knowing that the scene has been shifting ever so slightly since the night our great-great-great-grandparents looked up. It's not that the sky is different from one generation to the next in any dramatic way, but it is changing in a gentle, inexorable way that becomes visible only when you step back and measure across eras. That connection between the immediate stability we rely on and the slow-motion evolution playing out over geological time is one of the most beautiful aspects of celestial mechanics. Next, we'll look at how some of these long-term changes show up in specific examples, from the asteroid belt and the rings of Saturn to dramatic migrations in exotic exoplanet systems, and what they tell us about how planetary systems form and survive. Imagine the opposite for a moment. Gravity just stopped. Not slowly fading, not weakening, but in one impossible instant, the sun's pull is gone. No invisible hand tugging on the planets, no steady centripetal force curving their paths. What happens next is simpler and more violent than you might think, and oddly familiar if you've ever let go of something while it was moving. Think about swinging a ball on a string around your head. The ball traces a circle because the string keeps pulling it toward your hand. Let go of the string and the ball doesn't spiral into the sky or hover above you. It flies straight off in whatever direction it was moving at that exact moment. That straight line escape is inertia. Objects in motion stay in motion in the same direction unless forced otherwise. Now scale that up to the size of planets. At the moment gravity vanishes, each planet keeps going in the direction it was traveling, but that direction is tangent to its previous orbit, not toward the sun. Earth, for example, is moving sideways around the sun at about 30 kilometers per second. Remove the sun's pull, and Earth doesn't hang in place or float toward the center. It shoots off along a straight path at that same blistering speed. The elegant ellipses and circles we're used to would instantly become streaking, independent trajectories. There would be nothing left to make them curve around anything. The whole pattern we call the solar system would unravel like a spool whose thread suddenly breaks. That mental picture, planets peeling away along straight lines, does two things. First, it gives you a visceral sense of how ordinary and quiet gravity is. We rarely notice it because it's constant, like the low hum of a refrigerator. Second, it shows gravity's role as the system's glue. Without it, the sun's light still reaches everywhere, but light alone doesn't keep worlds in check. Gravity is the invisible architecture that holds together billions of kilometers of motion. If you watch this play out in your head, there are instant consequences, and then consequences that creep in over minutes, hours, days, and longer. Instantly, every orbit opens into a tangent. Moons stop circling their planets. Artificial satellites, the communications, GPS, and weather satellites we rely on, would no longer orbit Earth. They'd continue in straight lines at their current speeds, leaving the planet behind or intersecting it in unpredictable ways. Debris that used to be shepherded into belts by gravitational tugs would scatter. Within minutes to hours, on a human scale, things get personal and terrifying. On the surface of Earth, you'd still be moving sideways at 30 kilometers with the planet for an instant. You wouldn't be flung into space right away. You and the air and the oceans are all zipping together. But without gravity to hold the atmosphere and oceans tightly against the crust, pressure differences and the planet's rotation start to rearrange everything. Oceans would begin to slosh outward, forming enormous paths and blobs instead of staying wrapped around a sphere. Gradually, the atmosphere would thin and expand into space. Eventually, it would no longer envelop the planet in the familiar way that lets us breathe. Over days to months, with no sun-planet gravity to keep comets and dwarf worlds corralled, reservoirs like the Oort cloud and Kuiper belt would lose their custodianship. Cold, icy bodies would coast away on new trajectories that could cross paths with others. Collisions would become more likely in some places, emptier in others. The cosmic order that keeps planets spaced and stable would be gone. On human timescales, the most immediate threat isn't a planet vanishing, but the loss of everything gravity enables. Stable atmosphere, liquid water staying put, and the cycles that sustain life. Tides, driven by the moon's gravity, would vanish, replacing a reliable rhythm with chaos. Seasons would be meaningless without orbital motion keeping a relationship between sun and planet. Even what counts as sunrise would change because planets would no longer be in steady orbits that define days and years the way we know them. It helps to bring this back down to something you can feel. We take gravity for granted every time we stand up, pour a cup of coffee, or drop our keys. It's so mundane we rarely give it a thought. But that mundane force is exactly what keeps the solar system from turning into a scatter of space debris. Without that quiet tug, everything big, and many things small, would prefer to go its own way. There's also a surprising takeaway about stability. Orbits feel delicate, but they're also robust in a way. A small push won't send a planet careening away because gravity continuously corrects the motion. That's why spacecraft need precise burns to change their orbits. The sun's gravity doesn't let things wander willy-nilly. Turning gravity off is an all-or-nothing change that shows how essential that continuous correction is. It's not that the planets are glued in place so tightly they can't move. It's that their motion is constantly guided by gravity, so they follow predictable curved tracks instead of straight escape routes. And there's a poetic side to this thought experiment. Picture standing on a mountaintop as Earth begins to slide away on a straight path. The sun would appear to shift slowly, not because the sun moved, but because your backdrop for motion changed. You'd realize how intimate the relationship between a star and its planets is, not just light and heat, but an ongoing tug-of-war that sculpts motion across the cosmos. Gravity is the silent choreographer setting the steps. So, when you next glance up at the night sky and trace the path of the moon, or the slow drift of the planets, remember that what looks like a serene cosmic dance relies on one invisible rule. Take that rule away in your imagination, and the dance becomes a scattering. That thought experiment doesn't just teach orbital mechanics, it helps you feel how fundamental gravity is. It's the quiet glue, the background certainty that lets everything from apples to planets behave the way they do. Now imagine the other extreme. Keep gravity exactly as it is, but erase the sideways motion, the tangential speed that keeps a planet circling. If Earth suddenly stopped moving around the sun and just hovered in space, gravity wouldn't wait politely. There would be no graceful curve, no orbit at all. Gravity would pull straight inward and Earth would fall. That's the heart of the thought experiment. An orbit isn't some mysterious force that cancels gravity. It's simply a balance between two things: the sun's pull inward and the planet's tendency to keep moving forward. Take away the forward motion, and there's nothing to provide the sideways component of the constantly curving path. Instead of perpetually missing the sun, the planet drops. Think of it like this. When you ride a bike and suddenly slam on the brakes, your body keeps wanting to move forward. That want is inertia. In orbital terms, the planet's inertia is the sideways motion. Gravity provides the inward pull. In a stable orbit, those two effects exactly match, so the planet is always falling, but always missing. Remove the sideways motion and you simply fall straight in. What would that fall actually look like? A few things to picture. Acceleration and speed. With no tangential velocity, Earth would accelerate toward the sun under gravity and pick up speed as it fell. There's no gentle spiral at first. It's a radial plunge. Timescale. Surprisingly, falling from Earth's orbit to the sun, if you started from rest, wouldn't take centuries. Using the math for a body falling radially under gravity from one astronomical unit, 1 AU, into a mass like the sun gives a time on the order of a few months, about 65 days. That's because gravity grows stronger as you get closer, so the fall speeds up dramatically. Energy and heating. All that gravitational potential energy converts into kinetic energy as Earth falls. By the time it reached the sun's outer layers, it would be moving at hundreds of kilometers per second. That energy has to go somewhere when Earth slams into denser solar material, intense heating, vaporization, and a huge release of energy. Earth wouldn't hit the sun like a cold rock. It would be shredded, heated, and essentially turned into a hot plasma long before reaching the core. What would Earth experience? Long before physical contact, Earth's surface environment would be ruined. As the planet got closer, sunlight intensity would increase enormously, boiling oceans, stripping the atmosphere, and breaking apart rocks. Tidal forces, the differential pull on the near and far sides of the planet, would grow as well, possibly ripping the planet apart if those forces exceeded the structural strength of the crust and mantle. In short, catastrophic destruction, and on surprisingly short timescales compared to human history. It's tempting to ask, could Earth actually stop like that? Physics says no, not without a colossal exchange of momentum. Angular momentum is conserved unless acted on by an external torque. To halt Earth's orbital motion instantly would require an enormous torque, or a transfer of that angular momentum to something else, another massive body, or an equally enormous exhaust of propellant. There's no practical mechanism that could do that in an instant across an entire planet. So, the scenario is physically unrealistic, but useful. It highlights that orbits are not stable because gravity alone cancels out. They're stable because of motion. If the sideways motion were only partially reduced rather than removed, the result would be different. Instead of plunging straight in, the planet would spiral slowly inward. That's what happens in real astrophysical systems when angular momentum is drained. Gas drag, Interactions with a protoplanetary disk, tidal friction, or close gravitational encounters can sap a planet's sideways speed and make it migrate toward the star. In disks around young stars, that process helps explain how planets can move significant distances from where they formed. But to cause a direct radial plunge, you need nearly complete removal of the tangential velocity. There are some helpful analogies to make this feel immediate. Imagine you're standing on a perfectly frictionless ice rink and toss a ball so it glides in a straight line. Now picture a giant invisible hand that suddenly stops the ball's sideways motion. The ball would drop straight down if there were gravity acting inwards. Or think of being in a small spacecraft orbiting the Earth. If the astronauts suddenly fired retro rockets to cancel the craft's orbital velocity, the craft would fall and eventually re-enter. Pilots and engineers actually do the reverse routinely. They fire rockets to change speed and thereby change orbits. What you accelerate or decelerate is what determines whether you keep missing the planet or fall toward it. One last, slightly unsettling but personal way to relate. Imagine if one morning the sky didn't look different, but the sun started to grow noticeably larger each day. That's what a planet falling inward would look like from the surface. A rapidly brightening, heating sun, and a planet that's being cooked from the outside in. Nobody would have centuries to prepare. The grace disappears fast when you remove the sideways motion. So the takeaway is simple and surprisingly poetic. An orbit is literally a perpetual fall, but a fall that keeps missing because the planet is always moving forward. Take away the forward motion, and the loop vanishes. You need both the pull inward and the tendency to move forward. Remove either, and gravity's elegant ballet turns into an all-too-real plunge. Picture this. You're at the playground, you grab a length of string, tie a small rock or a key to the end, and start swinging it around. The rock wants to fly off in a straight line. That's just how things behave when nothing else acts on them. But your hand holds the string, and the string keeps tugging the rock inward. The tug doesn't let the rock go straight. Instead, the rock keeps falling around and around in a circle. That simple tug and motion combo is the same basic trick that makes curved paths possible. When I was a kid, I used to do this for hours, sometimes with a stone, sometimes with my little brother's plastic dinosaur. And I didn't know I was learning physics. All I knew was that the harder I swung, the tighter the circle looked, and the more I had to grip to keep the string from snapping out of my hand. That harder I swung feeling is exactly the point. The faster the object moves, or the tighter the turn you try to make, the stronger that inward pull has to be. Take a car as the next, slightly more grown-up example. When you steer around a bend, the car doesn't magically change direction. The tires push against the road, and the road pushes back. That sideways push is friction. Friction is the inward force that bends the car's straight-line motion into a curve. If you go slow and gently steer, there's plenty of friction to keep you on the road. But if you speed up too much for a given bend, or the pavement is wet or icy, the tires can't generate enough inward force and the car starts to slide outward. You feel like you're being pushed away from the curve. That feeling is your body's inertia. It wants to keep going straight while something else is dragging you inward. You've probably felt that while riding a bicycle too. Bikes are interesting because you don't just steer with the handlebars, you lean. When you lean into a turn, you're aligning the forces so that the combination of gravity and the inward push from the ground keeps you from toppling over. Visually, it makes sense. The bike and rider tilt, so the net force points through the center of mass. Practically, the faster you go, the more you have to lean to make the same turn. That's why sharp, high-speed turns look dramatic. The inward pull needed is large, so your whole body tilts more. There are other small, satisfying demonstrations you can try at home. The classic is a bucket of water. Swing it in a vertical circle, and if you do it fast enough, the water stays in the bucket even when it's upside down. The water wants to fly off in a straight line, but the bucket constantly accelerates the water inward, so it keeps moving along the circular path. It's an easy way to see continuous inward acceleration in action, and it felt like a party trick every campsite I ever went to. Do it carefully. Don't swing a half-full coffee mug over anyone. None of these examples is a perfect model of a planet orbit. The rock on a string behaves differently because the string is a physical contact pulling on the rock, and the car's turn relies on friction between rubber and pavement. Gravity, by contrast, is a long-range force that acts without contact across empty space. But the intuition you get from the everyday examples still maps over. You need a steady inward influence, and you need forward motion. Replace the string with gravity and the rock with a satellite, and the same combination, continuous inward pull plus motion trying to go straight, makes a looping, curving path instead of a straight line into space. There's a nice way to feel this mentally. Imagine throwing a ball as hard as you can horizontally. If you stand on a high cliff and toss it gently, it will fall and land somewhere below. Throw it harder, and it goes farther before it hits ground. Throw it so hard that the ground curves away under the ball at the same rate the ball falls, and the ball never hits the ground. It keeps falling around Earth. That's orbit in a sentence. On Earth, gravity plays the role of the inward tug that keeps the object turning around instead of escaping straight away. Back at ground level, this is why highways have banked curves and why race drivers and motorcyclists train so much. A banked curve changes the geometry, so part of the road's push is already pointing inward, reducing the amount of friction needed from the tires. That's also why you slow down on a slippery curve. Lowering your speed reduces the inward force required to stay on the arc, so less friction is needed and you're less likely to slide off. There's an emotional side to these experiences too. The little thrill on a roller coaster, the stomach flip on a sharp turn, the tiny moment of fear as your car starts to drift on wet pavement, all come from your body recognizing the mismatch between the straight line motion it expects and the inward force that's actually being applied. That sense of being pushed outwards while some invisible thing pulls you inwards is an everyday hint that objects prefer straight lines unless something makes them curve. If you want to make this even more personal, try a small experiment. Tie a set of keys to a shoelace and swing them around while standing in place. Pay attention to what changes when you swing faster or when you shorten the lace. Notice how much more you have to grip as the required inward pull grows. Or next time you're a passenger in a car, consciously feel the push into the seat and the lean of the vehicle when the driver takes a corner. Try to link that to the idea of motion trying to go straight and a force constantly redirecting it. That everyday intuition, tug inward, object tries to go straight, is the bridge between playground physics and planetary motion. It's not the whole story, but it's a powerful starting point. Once you've felt and seen this idea a handful of times, the leap to thinking about moons and satellites as things that are falling around a planet stops feeling strange. You've already been learning orbital ideas on the swing set and at the wheel. The sky just uses the same logic, working on a much bigger scale and with gravity doing the pulling. There is something quietly reassuring about orbits. They mean that motion and pull, chaos and order, can reach an agreement that lasts for ages. Earth will not slide into deep space tonight. It will not crash into the sun tomorrow. It will keep following the same path, gently changed only by long-term effects. Our days and seasons are built on that stability. When you look up at the sky and see a bright planet, you are glimpsing a world held in a kind of cosmic routine. It is always falling, always moving, and yet always returning. Think about how that plays out in the small stuff of your life. We wake up because the side of Earth we're on rotates into sunlight. We plan vacations around predictable seasons. Farmers plant with a calendar that has been reliable for generations. Sunrise and sunset are the most basic metronome we have. That steady beat is not just poetic, it's practical. Whole cultures, rituals, and economies evolved around the expectation that tomorrow will look and feel a lot like today. There's comfort in that continuity. It lets us build houses, raise children, make promises that mean anything beyond a single day. I still remember a night on a camping trip when I was a kid. The sky was so clear the Milky Way looked like spilled sugar, and a bright star moved more lazily than the others. My dad pointed at it and said, "That's Jupiter. It's been in the sky like that since we were kids, and it'll be there for your kids too." It wasn't scientific reassurance so much as a human one. That tiny fact, a dot holding to its path for millions of years, made the rest of our noisy, unpredictable world feel steadier. You've probably had a similar moment, lying awake during a storm, glancing at a familiar constellation and feeling oddly calmed by the idea that those patterns will outlast whatever's worrying you. Orbits are the universe's promise of predictability. Newton's picture of always falling, an object so fast it never hits the ground but keeps arcing around, captures the paradox. Motion keeps things in place. That idea is both poetic and functional. The moon's orbit creates tides that, over eons, shaped coastlines and influenced life's evolution. The tilt and orbit of Earth give us seasons, which set the rhythm for ecosystems and human activities. Even tiny, precise orbits of satellites let your phone find directions in seconds, and meteorologists track storms. That satellite beeping your location and the heartbeat of climate models both depend on the same basic physics. Bodies in orbit tend to stay in orbit. There's also a kind of emotional math to it. Life throws curveballs. Illness, loss, career changes, sudden news. Yet when you step outside and the sun still comes up, when the moon still waxes and wanes, it's like a soft promise that not everything is up for instant rearrangement. That doesn't make problems smaller, but it gives context. The world has rhythms longer than our panic cycles. When you feel overwhelmed, grounding yourself in those larger patient cycles can be calming. The seasons will change, tides will rise and fall, the planet will keep its path. That steady background makes room for us to act with less frantic energy. Routines and rituals fill the same psychological role. We pick a coffee mug because the ritual of brewing is a small orbit in our day. We schedule weekly calls with family because the return motion of that appointment creates continuity. Orbits are the cosmic equivalent of those rituals, a reminder that returning is possible. The idea that motion can be repetitive without being static resonates with how we want our lives to feel, alive and changing, yet anchored. Of course, stable doesn't mean frozen. Orbits evolve. Earth's axis wobbles slowly. Orbital eccentricities drift. Planets tug on one another over eons, and sometimes a comet or asteroid can alter things. Those changes happen on timescales far larger than a human lifetime. That slowness is part of the comfort. The universe changes, but it doesn't rewrite the rules overnight. Even when big changes come, ice ages, mass extinctions, continental drift, they are processes you can study, learn from, and sometimes prepare for because they are gradual, and for the sort of everyday comfort we need, the routine holds. There is also something democratic about orbital comfort. It doesn't belong to one person, nation, or culture. It's available to anyone who looks up. A farmer in the same time zone, a child in another continent, and an astronaut in orbit share the same sky and the same expected motions. That shared predictability builds common ground. Calendars, holidays tied to solstices and equinoxes, navigation by stars. These are cultural practices built on reliability. When ships' navigators used the stars to cross oceans, they were trusting orbits to keep their bearings. When communities celebrate harvests, they are thanking orbital regularity that made agriculture possible. And orbits are comforting in a visual, almost cinematic way. There's an elegance to a planet tracing a clean curve against the black. Its choreography on a scale our daily lives seldom touch. Watching a satellite pass overhead or tracking a bright planet through its slow motion night after night brings a sense of order. It's like watching a friend arrive on time. The predictability lets us plan little joys, a comet's return, a predictable transit, the way Mars becomes especially bright and easy to find. Those small, assured spectacles link us to longer timescales and to people who looked up before us. On a technological level, that assurance enables modern life. Airlines compute trajectories, knowing Earth and its satellites behave reliably. Power grids and agricultural markets depend on seasonal patterns. Space missions, from weather satellites to Mars rovers, are built around confidence in orbital mechanics. Imagine a GPS that might change its mind about where satellites will be tomorrow, or a calendar that could randomly shift months. Our lives would be immeasurably more chaotic. So, part of the comfort is practical. Orbits make complicated systems possible and dependable. Finally, there's a quiet moral about control and humility. We can't command the planets, but their steady behavior gives us a scaffold on which to build meaning and structure. That's humbling and comforting at once. We get to live within a system that's old and vast, and that frames our brief dramas without denying them. The cosmos doesn't promise immortality, but it promises continuity. And that continuity, the idea that motion and pull can negotiate a lasting compromise, gives a strangely human kind of assurance that some things persist, that cycles return, that even in change there is pattern. So when you next glance up and see a bright dot trailing its path, let that small silent motion do some of the heavy lifting for your nerves. It's not about ignoring problems. It's about standing in a rhythm larger than yesterday's crises. Orbits remind us that motion can be reliable, that falling can mean staying, and that a world in motion can also be a home. Feel your body still while the planet beneath you races on its silent track. Gravity pulls inward, motion wants straight. Together they make the gentle curves planets follow. They neither escape nor fall in. They keep missing and circling. Breathe slowly. Picture those steady paths around the sun and let that ancient balance lull you into sleep. Feel the calm in that motion now.